Hello. Yeah, hello students.
Yes, sir. Hello.
Yeah. Am I audible? Hello?
Yes, sir, you're audible.
Okay, good. Yeah, right. Okay. So let me share the presentation first. Yeah, is this slide visible? Hello?
Yes.
Yes, sir. Yes, sir.
Yeah, good. Okay. So like in the last lecture, actually we are discussing about processes. So any questions regarding the process, right? So any questions, anything? Okay. So so if you remember, actually last class, yeah, last lecture we started this the concept of process and like various states the process visits during its journey, just from creation of a process to termination, like various states, and then how these states are connected, like how the process transitions from one state to other state. So all these things we discussed, and along with that we also discussed like when this process switch, like when the CPU switches the process from one process to other process, so whether it may be user process or operating process and all, operating system process, like what are the various things that happens and all, basically during the context switch time. So those things also we discussed, and one another important thing is that, so the important attributes of, or you can say the control information related to a process is maintained by the kernel, and it's known to be a process control block. So where it maintains the different entities related to a process, like process identifier, right? And then the state of a process, and the contents of registers, CPU registers, and what are its so which process has generated this one, like it means a parent process, and if there are any child process, what are the child process, right? And the memory management information, and the list of files that were opened. So all these details like related to a process is maintained by uh, in the form of a data structure, and it is maintained by kernel in its kernel's address space. And so you can see this is the way the like the structure of a process control block look like. So these are the various attributes it contains, like yeah, its name is like a task struct, right? So the task is like, no, it's as I told you like earlier, like a process job. So the same way in the Unix terminology. So it's another one more term related to similar to the process and known to be task and all. So task struct, and in that there are various attributes and all. Here you can able to see process ID, PID, and the state of a process. It will be a long integer, and the time slice that will be allocated to a process and all. So that is of integer type, unsigned integer. So likewise, there are various attributes like parent, because the parent is also a process. So therefore, the details of a parent, and it has a pointer to that, and it is pointed to a parent process. So therefore, the task struct, because the parent is also a process. So therefore, it is indicated by task struct, right? Likewise, the children also, and the files that are list of files that are attached to this particular process, and then the memory management information. So all these attributes are part of the a process control block, and whatever the process that are there in the which are there in the main memory and all, so they are connected, or they are like maintained in a data structure in the form of linked list data structure, doubly linked list data structure. You can able to see that. And in that, whichever the current process the CPU is executing, and that's where the current pointer is located to. The pointer is located to this particular process. It means that, so whichever the control block this particular pointer refers to, it means that this particular process is currently executing under the execution of the CPU. Okay, yeah. So the and here then the next thing is that concept of process scheduling. So process scheduling means, as we aware that there are several processes so that are in the main memory, and they used to be run by the CPU or executed by the CPU. So therefore, this list of a process will be waiting for CPU's execution, and there will be a list of process waiting for IO. There may be a list of process waiting for a specific files, for example, in the from the disk and there may be a list of process may be waiting for display their contents. So that way, inside the system, there are several schedulers used to be there that used to schedule a resource against to a multiple process and all. So that way, this is one of them. One of the important one of the scheduler will be like the CPU, like to maximize the CPU utilization. So we used to schedule the process, multiple process to the CPU, like one after another kind of a thing. And not only that, and as we know that nowadays, like most of the applications are interactive applications. So therefore, the CPU will allocate a fixed time slice, it's very smaller in size, so that like each process will get a fair share, like a small amount of time slice, so that you can see that we'll get a feel that like all the processes are running concurrently by the CPU, so that like the majority of a process where you can the user can interact directly from time to time, and for him, like it appears that all the processes are running concurrently and parallelly and all. But it happens like one after another in a time scheduled way. It happens. And a process scheduler, as you know that it selects among the available process, like for the next execution of a CPU, right? So that's what the process scheduler will be. And here the important the scheduling queues that are maintained by the operating system were, you can see here, job queue, ready queue, and device queues. So device queues means like that depending on what are the various devices that are uh, consisting of that are attached to a system and all. So for each device and all, to provide access to the various process and all, each device will maintain the queue. So therefore, these are the device queues. Like for example, suppose you have a hard disk. So therefore, there are lots of process needs the access from the like needs the file access from the hard disk. So therefore, the hard disk maintains the device queue. Likewise, a keyboard also. Likewise, a monitor. So that way, various peripherals, and likewise, suppose network adapter card, for example, where a process that want to connect through network and all. So they will be listed. They will be maintain a queue against the network output port. So that way, each device will maintain the queues. Those are nothing but the device queues. And the job queue and ready queue are these are reference to like the CPU. Like first of all, the job queue means the set of all processes in the system. It means that suppose a process want to execute, as we know that the way it happens and all, like by using a mouse, if you double click on that, then that particular process, that particular program will be loaded into main memory, and then it becomes a process, and then it will be ready for execution. So in the process, sometimes there may not be enough space in the main memory, but you want to run the process, you want to execute the process. So at that time, a program want to execute, want a program become a process, but there is not enough space in the main memory. At that time, the process, some number of process, they will be waiting in the disk itself. They will be waiting at the disk itself. So there is a job queue, that is a scheduler. There's a job scheduler, so which is used to maintain at the disk and all. So there it maintains a list of process, and those processes will be placed. They try to place into the main memory as and when you have available space is available. You have sufficient space that is available. So that way, the job queue is nothing but it's a queue or it's a scheduler is maintained at the disk, and the processor ready to place into the main memory. But due to the lack of space, the process will be there in the disk itself. So that is known to be job queue. Whereas a ready queue is nothing but set of all processes residing in the main memory. That means the processes that are there in the main memory, and now they have been given a chance to the CPU from one after another and all. So those processors will be available or will be placed in the ready queue for its turn to execution by the CPU and all. So they will be waiting in the ready queue, and then whenever they get a turn, and then that turn they will get access to the CPU, and the instructions of that process will be executed. So likewise here the job queue and ready queue and all. So these two are somehow related to the schedulers that are used for the process execution and all. And the remaining device queues are that for each device it maintains a queue because it's a single device or finite number of devices and all. And there are many more processes used to access the devices. So therefore it has its scheduler, and the scheduler will maintain the queue, and then the queue will be served like one after another by the device and all. And the process will migrate among the queues, right? For example, if a process in the CPU in the main memory, so it may first of all it need to execute. So therefore it will be given access to the CPU. Then during the execution, maybe some IO command or IO instruction will be encountered. So with that, the process will be suspended, will be taken out from the CPU, and whatever its requirement, accordingly, it will be placed in the appropriate device queue. So likewise, so once that again the device, once if the IO request is completed, and again this process now the IO is completed, now again it needs some more execution from the CPU by the CPU. So therefore it will be placed into the ready queue. So that way, at any point of a time, the process will be in one of these queues, either in the job queue or in the ready queue or in the one of the device queues. So it will switch between the various queues that are present, that are maintained by the operating system under. All these queues are maintained by the operating system. And this is the way the queues look like. You can say that because here the processor waiting in the queue means it's not that because each process is like monitored, or it can be like the entire information, mostly the control information is maintained by the operating system in the form of PCB. So these PCBs will be placed or will be pointed to appropriate queues. For example, you see this is the ready queue. So at this point of a time, the ready queue contains the two processes. One is the process 7 and process 2, right? And here it maintains in the form of in the form of linked list, where it has two pointers, head and tail. Head pointer is pointed to the first process that is immediately to the head, that is at the beginning, and the tail process points to the last process that is in the queue. And here these are the queues corresponds to magnetic tapes, and this is the disk like a disk 0. Likewise, we have, suppose there are multiple disks, we have multiple queues will be there. Likewise, we have different terminals. So like these are the examples where how the various devices or various queues are maintained. And here, first of all, queue means the maintaining a queue is nothing but like the list of processes, the PCBs that are attached to a specific device queue and all. So this way, the queues will be maintained by the operating system, right? Okay. Then this was the overall picture, a broader picture. This is if you look at this particular picture, you can see all possible different queues and all possible places where the process can stay, process can be reside. Either the process may be in the ready queue, or it may be in the execution, or it may be in the waiting for IO, or it may be, for example, process is in the CPU. Then when the timer interrupt arrives, right, or its a time slice is over, then immediately the process will be taken out from the CPU, and then it will be again brought back to the ready queue. Or the process may create a child, then the child execution takes place, and then afterwards the child also will be placed in the ready queue. And the process may be sometimes, no, it may be waiting for certain signal or some event to happen. At that time, when that event happens, that is nothing but the corresponding signal arrives, then the process again will be go back to its ready queue. So this particular diagram, if you look at, this is somewhat, it's like more or less the illustration of a process state diagram in another way. Like in case of process state diagram, we have seen that what are the various states the process can visit and how these states will transit from how these states will change from one state to other state and the possible transitions and all. So here it is almost similar to that, but instead of states and all, we here will mention about what are the various queues or what are the various resources that are there. So that will be placed that are like shown over here and all, right? Here these are the queues, right? The rectangular ones and all, and here the circular ones are the kind of resources and all, right? So this is the way you can able to see either that means in the ready queue or at the execution or waiting for IO, or when the timer interrupt occurs, at that time it will again go back to the process will be like suspended from the CPU and again it will be placed in the ready queue, right? Because the process, because it was stopped because its time slice is over, right? So because of that, the process will be again sent back to ready queue. Then the process may create a child, and now the child process will be started and its execution, right? And then the process may wait for some event to occur. So this way, this particular diagram is like just illustration of the where the process can reside in its lifetime. Then coming to the various schedulers, the important schedulers, and here we'll try to focus on schedulers related to the CPU. That means allocating the CPU resource or the CPU to the process and all. So where we have seen that there are two types of schedulers may exist. One is the short-term scheduler. It's nothing but CPU scheduler. And other one is a long-term scheduler or job scheduler. Long-term scheduler or job scheduler. So the CPU scheduler is nothing but the scheduler used to maintain the ready queue, right? So which of the process need to be placed in the ready queue, and what is the order, and what is the scheduling policy at which the queue has to be maintained or the process has to be allocated to the CPU. So that will be carried out by the short-term scheduler, or you can say CPU scheduler, or it is nothing but the process that are present in the ready queue. So what way it will be scheduled or which process or what are the priorities. So all these things will be maintained by a CPU scheduler, also known to be short-term scheduler, because here the CPU scheduler will be faster. Will be faster means actually you see that the CPU will be allocated to the process at a fixed time slice, right? It will be order of milliseconds and all. It means that for every certain fixed number of fixed quantum time slice, the scheduler has to take a decision. What will be the next process to be given to the CPU and all, right? So therefore, this is known to be short-term scheduler, and then it will be like it happens. The scheduler will have to make a decision very frequently from time to time. That is in the order of time quantum of milliseconds, maybe order of like 100 milliseconds. Suppose time slice equals to 100 milliseconds. It means for every 100 milliseconds, the scheduler has to make a decision. So in that context, we have to see that the overhead that is imposed by the scheduler should be as minimum as possible. That means it should make decisions faster. You see that the time slice that is itself is 100 milliseconds. So in comparison to that, to make a decision by the scheduler to allocate which process to be allocated next, so the decision process has to be much faster compared to the time slice that will be allocated for each of a process and all. So therefore, in case of short-term scheduler, so we need to see that the scheduler action, or like whatever the time that is required for the scheduler to make a decision, like, or the switching time should be as minimum as possible. And because this happens very frequently, because most of the current processes are they are the interactive process and all. So therefore, they are the time sliced. That means the CPU will be providing the access in a time sliced manner. So in that context, the short-term scheduler should be very fast. And the other one is the long-term scheduler. And here the long-term scheduler will be, as I mentioned, it selects the process like which need to be placed into the ready queue. That means the ready queue will be there. And then when what is the next process to be placed in the ready queue? So that will be the job of a long-term scheduler. And here the process to be placed in the ready queue, that depends upon, right? So there are certain number of processes already there in the ready queue, and the ready queue will be vacant, or ready queue will be available, a slot in the ready queue will be available. There are different occasions when the process, when there are multiple processes waiting for IO. At that time, the ready queue have some space, or otherwise a number of processes that are there in the ready queue, some of them will be naturally terminates. That means they reach to the last statement. So at that time, the process will terminate. At that time also, the ready queue have some time slice where some vacant slice where you can be some new process can be allocated. So altogether, the long-term process will take, that means will the its action or the scheduling decisions will takes place not that as frequently as the short-term scheduler and all, but here it takes quite longer time interval. So in that time interval, it has to decide that what will be the next process to be placed into the in the ready queue and all. So it will be compared to the short-term scheduler. It invokes very infrequently, right? In terms of sometimes it may take seconds or minutes also. So it will be slower slightly. But the long-term scheduler, one important responsibility of a long-term scheduler will be it tries to control the degree of multiprogramming. Degree of multiprogramming. So it means that, so whenever, suppose if you have enough number of processes are there in the ready queue, then the long-term scheduler will not invoke any process to be placed into the ready queue. And if that number of processes are less, for example, at that time the long-term process will try to fill up the ready queue, so that always the CPU has some process to execute. We should not, because the CPU is a very prime resource, very valuable resource. So you have to make sure that all the time the CPU should be always busy as far as possible. So therefore, this long-term scheduler is to control the degree of multiprogramming. It means that actually it tries to make sure that like given like it should tries to provide a fair chance to the multiple programs, so that each program should get enough time or like fair chance to visit the CPU, and it should some progress has to be made with respect to each of a process and all. So therefore, it controls the degree of multiprogramming. That's the main responsibility of long-term scheduler and all. And for doing that, actually, it has to see that what will be the nature of a process and all. Like, for example, when you see the process, that depending upon the application, some processes are like they are IO bound process. It means that during its execution, most of the time the process will spend for like will be attached to the IO device and will be like, for example, copying a file. For example, if you take the process like a copying a file from one file to the other file and all. So at that time, that particular process mostly involves with like the copying the contents from one file to another file. So where it involves most of the times it will be IO, right? And very few occasions it visits the CPU. Very few computations are required. Other than that, most of the time it requires the IO, right? It will be attached to IO devices, and with that, the desired data transfer will take place. And there are certain processes which are mostly the CPU intensive. It means that it indicates a lot of, it consists of a lot of computation is involved. Like, for example, the task related to that scientific applications. Or for example, if you take some mathematical application like computing a factorial of a number and all, or like generating some like some number, some sequence and all. So in that case, actually, we need to like mostly it's like a number crunching. It means that it's like a lot of times the ALU requirement will be there. So therefore, most of the times most of the its execution of a process will be involved with the CPU itself. So those processes are known to be like the CPU bound process and all, right? IO bound process means like most of the times the process needs the like requirement of IO, or the other ones are the CPU bound process and all. And you should have a proper mix of these two processes when you are allowing a multi-programming. Because suppose if you take the if most of the processes are IO bound process, then the CPU will be idle, because most of the processes are waiting at the devices and all, and because their basic activity will be the like IO. So therefore, all the process will be waiting for the IO. So at that time, the CPU will be idle. And likewise, for example, if most of the processes are CPU bound process, for example, so like the device queues or the devices will be like idle, like other devices or other resources will be idle, and they will be like their queues are empty and they are waiting for like for giving the service and all, but there is no process want to take that, right? So the either way is a problem. Like therefore, you should have a proper mix of IO bound and CPU bound process are required and all. So that will be done by using a long-term process and all, long-term scheduler. So therefore, if the among the process, if more of them are IO bound process, then the next process to be placed into the ready queue will be like a CPU bound process, some of them, so that the CPU and other devices also will be busy, right? So that way, the long-term process will try to see that it maintains the degree of multi-programming to a reasonable extent, so that all the resources will be utilized effectively. And there is another scheduler known to be like a medium-term scheduler. Here, these will be there. This requirement of this particular medium-term scheduler is required in case if there is no long-term scheduler. So at that time, we require the medium-term scheduler. So its basic job is to like whatever the long-term scheduler will perform, more or less to some extent, its responsibility or its objective is that one. So it means that, for example, a memory contains, or in your memory you have lots of processors for there, but there are certain processes they are not at all getting a time slot, or they are not getting a chance to like enter into the ready queue at all, right? So at that time here, the medium-term scheduler will pick up a process, certain process, they will be swapped out from the main memory, and then after some time they will be again swapped in and out. So that way it tries to see that it will give a fair chance to all the processes that are present in a main memory, so that there will be like a progress. You can able to see a progress in execution across the processes that are present in the memory and all. So that way the memory, the medium-term scheduler's job is to that. So depending on requirements, sometimes the process that are there in the ready queue will be swapped out of the memory, will be swapped out of the main memory and will be placed into the disk for some time. And then after that again, they'll be placed back into the main memory and all. So that way the medium-term scheduler, by using swapping, it tries to maintain the degree of multi-programming and see that the execution will be carried out in a fair way, or will be execution. It sees that all the process will maintain the will progress a reasonable extent that are present in the main memory. Okay. The next thing is that so far we discussed about different process states, and then how the processes are scheduled for various sources. And among them, we'll try to focus more on the CPU, right? And then along with the CPU, there are other resources will be there. And for that, there also, the process will be scheduled by appropriate scheduler. And all these schedulers will be maintained by the operating system. And they are part of the operating system kernel routines and all. And then in the process, when you are discussing about process, there are some important operations that are required, that need to be performed over a process. So these are the two important processes. One is the creation and termination. Creation and termination. And the process creation, process termination. We'll see that what these are. And here, the process creation is nothing but, suppose you want to run the process. We know that for execution of a process, we'll try to, using a GUI, the user will double click on that process, on the program. Then that program will be turned into a process. That means the program will be loaded into main memory. And if there is a chance, if there is a space available in the ready queue, then it will be placed into the ready queue for its execution. So it means that we are creating a process. That means by double clicking on the in the disk on the program. So it means that the program will be brought into main memory and will make that as a process. And then the process will be given access to the CPU in a later point of time. So here, it means that for doing that, what we do is that actually a process will be created. A process will be created by some process. So with that, a process are created. So therefore, here in this case, actually the terms like parent and child will be a process whichever is initiated for creation. So that process is going to be parent process, and then process whichever is created, it's going to be child process and all. It's like normal terminology, like whichever creates a process known to be parent process, and the created one, the resultant process whichever is created, so it's not to be child process. And again the child process may further again create a process, like at that time this child happens to be parent to the whatever the created process. So likewise, if you keep on the creating a process in a chain fashion, so you can see a tree of process that will be evolved, like in a branched in a systematic way. So you can see a tree of process will be generated. So in your system, so like the way the processes are created, the operating system, by using these like operations like creating a process using this appropriate system calls and all, a process are created like one by one after another it will be created and all. So we'll see later point of time, we'll see that how the processes are created and all later on. And when you're creating a process here, generally a process is created and each process will be identified by a specific identity. It's not to be process ID, process identifier. It's like integer quantity. Each process has a unique ID will be there. It's not to be process ID. And then as you know that a process are created in that some process happens to be parents and some process happens to be child, and again the child will happens to be parent later on. So likewise it evolves, the process will be evolves, and then it appears to be like a kind of a tree process tree. We'll see that. And now coming to the resource sharing between the parent and the child process, there are various possibilities are there. When a process is created, you have a parent and a child process, and may happens that parent and child will share all the resources. Whatever the parent has a resources, that means whatever the files the parent has opened and whatever the resources the parent has, all these resources can be used or will be shared to the its created children also. So that is one option, like a parent and children can share all the resources, right? And then the child, there are some other case where a children will share only the subset of a parent resources. And sometimes the parent and child will not share any resources at all. Will not share any resources at all. We'll see that what are these different situations and all, right? So it means that while sharing the resources and all, there are different ways. There are like parent and child can share all the resources, and children will share the subset of the resources offered by a parent. And parent and child, after creating a child, and afterwards the parent and child will not share any resources at all. Child will happens to be a completely a new process where the required resources are entirely different from the desired parent and all, its parent and all. So that way, the resource sharing, we have a different options. We have a different based on the requirements where the either resources can be shared or may not be shared also. And then after creating a process, the relation between the parent and the child in the process in view of execution point of view, a child is suppose a parent, a process created a child. Now it becomes a parent process and a child process. Now how the execution will takes place. So sometimes a parent and child will execute concurrently. It means that, for example, let's start with to have only one process in the memory. And now that process created another process. Now you see that now we have two processes. So in your ready queue, there are two processes are there, right? Based on the priority or whatever. So whichever the process, either the parent process can execute or a child process, or it will take turns also. So what it means is that actually here that means after creating a child, both parent and child can execute concurrently. That based on the scheduler policy, whatever. And sometimes a parent create a child and afterwards it will see that the child will terminate. It will see that the child will terminate, right? So it means that the parent creates a child for a specific purpose, for a specific job to be carried out. And in that context, the child will execute that, and upon the child's completion of that process, then the parent will start its execution. Till that point, the parent will wait. And excuse me. Yeah, Yeah, sorry. Yeah. So in the execution perspective, as I maintained that the parent and child can have either they can after the child is created, both parent and child can execute concurrently, right? Or otherwise, if sometimes no parent after creating a child, parent will wait, parent will be blocked until the child is terminating. So here the reasons maybe the applications maybe the parent creates a child for a specific job to be done, and it waits for its job to be complete, its process to be complete, and once the process complete, then the parent can take a result of that or whatever, and then it continues. So in that case, the parent will wait till the child will terminate. So that way, the execution sequence of parent child will be either they can run concurrently or like after creating a child, the parent may wait and upon the child process completion, then only the parent can progress. Parent can start his execution later part. Yeah, this is an example of a process tree, whatever I just mentioned. And this is in the case of Unix system. And the first process that is created by an operating system when it's just loaded after it's loading, soon after loading, it creates a process. It's known to be init, that is initial process, right? And this process will further create the different processes. Like at the beginning, this init process will create, that means operating system itself will create the other process, like for example, login. And this login means actually login in the local machine. Like it will create a login, and this login it will create a shell, like it means a user interface like bash shell or whatever. And from this shell again, the users can able to like run the process. Like here you can see the PS, and then here the Emacs editor will be opened. So with that, the documentation can be done. And this is the process related to the operating system, like a kernel related operations to perform. Here it creates certain process which are maintained by the operating system and all. And there are some other process which are meant for, suppose some process they want to some users, suppose they want to connect through like some other systems through network and all. So for facilitating that, yeah, these are the process like secured shell, and the secured shell will create the corresponding shell, and then with that, the process can be created for networking purpose and all. So likewise, what I mentioned is that you have some initial process, and this process creates the other process. So likewise, the process will be created, generated, in a hierarchical way, and appears like a tree. And now you can see that. So you can see these are the child process at this point of a time. And for these two child, this is a parent process, and this becomes a child to this one. This becomes a child to this one. So likewise, there will be hierarchy, and some process are parent and some process are child. So likewise, we'll have a relation between the process used to be there. We'll see that how these processes are created and all, right? And as I mentioned, like when a process is created, the creator is known to be a parent process, and the created process is known to be child process. So again, with respect to address space, we had discussed about coming to the resources, how they will be shared, and coming to the execution point of view, how the parent and child will execute. So those things also will briefly discussed. And now coming to address space, like when the child is created, when the child is created, a process, suppose child is created by a process, and a process which creates the child is a parent process. It has certain address space. That means address space means that particular process. That means it's its data section, its text section, its stack section. That entire thing constitutes the total address space of the particular process. And when the child is created, the child's address space is obviously it will be different from the parent address space. That means assuming that the parent will be occupying address from 100 to 300, for example. And when a child is created, the child address space will be like at the beginning, the child address space will be something different from this. It's not 100 to 300. It will be some 500 to 700, the same amount. And then it will be duplicate in that address space. whatever is the parent entities are there, or the parent text section, data section, stack, everything. The same thing will be replica will be placed in the child address space also. So therefore, when the child is created, the child will be like at the initially at the first step, soon after creating the child is a duplicate of a parent. Child is a duplicate of a parent. Duplicate means because the address space are different, but the entities that are there in the address space, that is the text section, data section, stack, and everything, that will be exact same replica will be there. So when the child is created, the child will be exact duplicate of a parent. Then after that, suppose if you want that the child happens to be a different program, a different process all the way. So at that time, the child program, whatever the child that replica, whatever is there, that will be replaced by the desired program under. So the required program, whatever is actually to be loaded, so that will be placed or that will be loaded, that will be overwritten on the child process and all, child process. So these things will be carried out by using system calls, right? Because this will be handled by the operating system, not the user program or user routines will not do that, right? So here you can see that in the case of Unix operating system, fork is a system call used to create a process, new process. Fork system call used to create new process. And then after creating a new process, as I mentioned that you have a parent process and you have a child process, and the child is an exact replica of a parent. It means that whatever the content is there in the parent, the same content will be there in the child also, right? But you don't require that one all the time. Actually, you want to create a new process, right? New process and some new program has to be loaded and all. So therefore, but the way the process is created will be at the beginning when the process is created, the child happens to be the same as the parent process. But later, depending on the requirement, whichever the process you want to actually program has to be run. So that particular program will be again brought into and it will be placed in the child process. So for that, we used to use another system call known to be exit system call exec, and using this exit system call, it will be used soon after the fork system call because the fork system call used to create a child and that child will be the duplicate of a parent and all. And now if you want to keep a new program to be loaded, so whatever the desired program that to be loaded and all, so that will be carried out, that will be done by using exit system call. So using the exit system call, you create or you just load the new code, a new program into the child over the child, so that the child will become a new process, new program and the new process and all. Earlier, the child is nothing but a parent process in the different memory space, in the different address space. Otherwise, the child and parent are both are same, right? But now here, after that, by using exec system call, you will be replace the child process with the desired program and all, the desired program. So then after that, the child process will run. The child process will run and the parent also will run. If it is a concurrent execution, both parent and child will run one after another, whatever. And yeah, that way it happens. And now here, as I mentioned, no, there are different execution sequences can possible. One thing is that the both parent and child can execute concurrently, right? That is one way. And sometimes the parent created a process and then the parent will wait till the child completes or the child's execution is completed or child is terminated and all. So in that case, you can see here the fork system call where it is a parent and a child is created. And once after child is created, suppose you want to use the exit system call, some other process has to be loaded. So it means that use the exit system call and with the help of exit system call, the desired program that need to be loaded. So that will be placed in the child process and that becomes a process. And now that process, the new process, whatever is loaded, so that will be executed first. And upon its completion, that is nothing but exit. Exit is nothing but the termination of a process. So whenever it terminates at that time, then till that termination, the parent process will wait. That means the parent process after creating a child, it will not do anything. It just blocked. That means it's just waiting for an event to occur. What is that event? That event is nothing but a completion or termination of a child process, whatever it's created and all. And upon its termination, then the parent process execution starts. So this is one way. It's not that all the parent childs will go by this and all. So sometimes the parent and child will execute parallelly. Right? Yeah. Now, if you look at the example where how the in case of Unix like operating system, how this the parent-child how the child is created, and then how the parent and child will share the CPU, how the execution will takes place. That you can able to see by using the simple code. You can see here. Anyway, the PID is nothing but a process ID, and yeah, this is the integer type. And now you can see that suppose you want to create a child in a process. Suppose this main is a process. This is a program and nothing but a process and all. So in the main, in this program, you are creating a process. That means when you are executing a fork means this system call will create a new process. Create a new process, and initially that new process is nothing but the exact replica. Whatever is this entire program is there. The same content will be there in the child process also. In the child process also. Right. So therefore, you can see the system call, the fork system call, right? And then upon immediately after you call the fork system call, the fork system call results in a, is nothing but creating a process. Another process will be created with the exact replica of this one, with the exact replica of this one. The only change, the only difference between the parent process and the child process will be right. And when you are creating this child process, this fork will return. The fork will return something. So the fork, in case of parent process, it returns the process ID of a child will be returned to a parent process. Whereas the same fork, because as I told you, the child process also contains the same code. So therefore, there also we have a fork system. Fork used to be there. That particular fork system call, that particular fork will return in the child process as a 0, right? That is the only difference. Other than that, both parent process and child process will be exactly same. The only thing is that in case of parent process, after creating a child, that means this fork system call will return the process ID of a child, whatever the process ID of a child, right? It's a positive number. It's a number which is a positive integer. So whatever the unique ID that is allotted to a child process, so that process ID will be returned to a parent. The child process ID will be returned to a parent. Whereas in case of a child, this fork system call will return 0. So that is the distinction between a child process and a parent process. Otherwise, exactly the same. The entire code is exactly same, right? And then after this fork system call, you have two processes. One is the parent process, other one is a child process. Both are same. The only difference is that in case of parent process, the PID corresponds to the child's PID because it returns the child's PID. Whereas in case of a child process, this PID is 0. If a fork system call is successfully happens, in case of child process, it returns to 0. So that means the PID in the child process carries a 0 value, whereas in case of parent process, the PID carries some positive integer, some positive integer. So that is the distinction between a parent process and a child process. And now to coordinate the child process, to run the child process, for example, here after this process is created, the next will be like just to check that whether the PID is less than 0 or not. PID will be either 0 or greater than 0. It will be 0 in case of a child process. It will be greater than 0 in case of a parent process, because the parent process, in the parent process, the fork returns the PID or the process ID of a child process. The process ID of a child process will be some positive integer. So that will be returned in the parent process. Whereas in case of child process, this fork system call returns a 0 value. So suppose, for example, if the fork system call is not successful, due to some reason, the fork system call is not successful. At that time, the fork system call will return a negative number. The fork system call will return a negative number. It indicates some error is occurred. That means the fork is not successful. Some error or fork failed. So that was the indication if the PID is less than 0. That is, the PID is negative. If PID is negative, it indicates that it's a fork is failed. That means the fork system call is failed, right? Okay, and this is just to check, just to indicate that if in case if the fork is failed, it will be informed. It will we come to know by looking at this one, by with the display of this one fork failed and all. Because when the fork failed at that time, this returns the negative number. It is a negative number, negative value. So that with that you can come to know that the fork is failed. And if the fork is successful, it will be, and you can get either a PID will be 0 or you'll get either PID will be greater than 0. So the PID will be 0 is observed in the case of child process, and the PID will be greater than 0 you observe in the case of parent process. So therefore here you can see that in this code, when you're writing the code, you're creating a process, and here in the child process you can see that if a PID equals to 0, it means that you are just checking that whether the PID equals to 0 or not. If PID equals to 0, this is true in case of a child process. In case of a child process, because you see that the same code will be there. As I told you that initially the child and parent have the same code, except the value of a PID it holds, except the value of PID it holds. So therefore, if we are checking that if a PID equals to 0, then do this. It means that if it is a child process, then what you are doing in that, if it is a child process, then in the newly created process, you do the, suppose you want to run some new process in that. So therefore, using the exec system call exec, using exec system call, you are loading some other program into that. That means here you are loading a program known to be ls. Using program is a command. Ls is nothing but a program, a process. So ls will be there. Ls will be loaded, and now it means that what happens now here at this point of a time, till that you have a child process that is exact replica of a parent process. And now after this, once if you know that actually it's a child process, then we are executing this. We are executing this system call, exec system call. So with that exec system call, we are loading the desired program into the child memory, in the child memory space. So we are loading the ls. So now this is a new process, right? So now the child process contains a new process ls, right? So this ls, when it executes that, when the child process is executing, now this ls will be executed. It's nothing but it displays the list of the files under this directory, /bin at that time, and the /bin, whatever the files are there. So all these binary files will be listed out under. So that's the job of a new process. Then afterwards it will terminate. Afterwards the process will terminate. That is nothing but after that you have null. Null is nothing but you have no more. After you display that ls, there is nothing to do. There is nothing to do. Then the process will terminate. Process will terminate. And now he see that there is else is there. So else you need to, now you have to see the parent portion. Else you have a wait null. Wait null means here, that means during the, you see that why am this code is that you just try to think that because now you are creating a process, and with that the child process is created, you have a parent process. So the system will run, the operating system will run both the parent process and child process, because now assuming that you have only one process is there, it creates a process. Now we have two processes are there. One is the parent process, other one is the child process. So in the child, so both are like competent enough to, or both are like you have equal fair chances to allocate to the CPU and all. We don't know that actually which process will be allocated, whether the parent process will be allocated or a child process may be allocated. We don't know, right? So therefore, if a child process is allocated, for example, at that time, we need to load the new program and it has to be run as per the requirement, right? And if the parent process is there, then you have to skip this one, because if a parent process is running, for example, then what happens? It just checks that PID is less than 0. No, because in case of parent process, the PID will be greater than 0, right? PID will be a positive integer, right? So it's not less than 0. Then it checks this one, because it's not less than 0. Then it comes to this else portion. Then it checks that the PID equals to 0. So this is not, PID is greater than 0 because it's the parent, right? So PID is greater than 0. So therefore, this particular thing is not executed. And then comes to the else. And here it's nothing but wait. So it means that since it is a parent, because here otherwise if it is not a parent, if it is a child, then it will go into this one. Since it is a parent process, so therefore it will not go into this one. It will come and then it will come and it will wait. It just wait for null. That means null means wait for termination of the child process. Wait for termination, right? And it wait. That means now when the parent process is running, the parent process will just check this if, and then it will just check this one. And both these conditions are not true in case of parent. So then the parent process will wait here. That means the wait is it's again a system call, blocking system call. It wait for an event to occur. What is that event? That event is nothing but termination of a child, termination of a child. And so that way the parent process, when it executes, it will go on these conditions and it wait for the child to complete, right? And suppose take a turn, assuming that a child is there. So when the child, we don't know actually, as I told you, because both are exact replica. When the child is there, example, you can say that after the fork system call, because the execution starts here, because till this point, till before this fork system call, you have only one program and the CPU is executing this one. At this point, after this execution of this particular statement, there are two processes are there. There are two processes are there. And now among these two processes, that at that particular point of a time, the scheduler will make a decision and the scheduler can give a chance either to parent to continue or it may ask the child to continue. But for both of them, the execution starts from here. The execution, because here at this point of a time, a child has created. So therefore the pointer, the whatever the PC was there, now the PC points to here for in both the child as well as the parent also. It starts here. And now suppose, for example, if the process happens to be parent, then these two conditions are not, these two conditions will be failed in case of parent. So therefore the parent will wait here. And if this chance is given for a child, for example, then this is anyway failed because in case of a child, the PID will be 0. So therefore, because unless the fork is failed, then this is not true. Then in the case of child process, then this will be realized to be true. This realized to be true. So then the exec system call will take over. And then using the exec system call, whatever the process to be loaded, so that will be loaded here. And here the process to be loaded is ls. So this is loaded here and ls will be loaded here. And then it will be executed. And then it will be executed, right? Afterwards, suppose, for example, after ls, for example, then this particular child process turn is over, for example, its time slice is over. Then again, the parent turn will come. But the parent is waiting here because the child is not terminated. So the parent will be keep on waiting there only, even though it's given chance to the CPU, but it tries to give a chance to CPU, but the parent is waiting. Parent is not in the ready queue. So therefore the child will continue. Next slice also child will come, right? And the child will complete this one process because ls is nothing but simple. It's a simple command. So the child it displays the contents and then afterwards it terminates. Afterwards it terminates. After it terminates means what? That means soon after this display, there will be some exit statement which is to be there. So the child process will be stopped. The child process will be terminated here, right? Then once the child process is terminated, the status information will be passed to the parent because the parent is waiting for the child's completion. So the child's completion status, whatever is there, whether it's a normal termination or abnormal termination, whatever. So it will be informed or it will be informed through the wait system call. The wait system call is blocking system call. It is waiting. The process, the parent will be simply waiting for some signal or some event to occur. That event will be result of the termination of the child. And once the child is terminated, then the corresponding termination signal will be reached to the through this wait system call. Then the parent will be unblocked. Unblocked means the parent will be come out of the wait and then the parent's execution starts. So the parent next statement here is that the child complete, right? So that way the parent and child will coordinate by using these PIDs and all. So how do you get this PID? These PIDs are nothing but when the fork system call is executed, at that time the fork system call return the value and returns the different values for parent and child. For a parent, it returns the PID of a child will be returned, whereas for child it returns the 0 simply, right? So that is the actual distinction that makes with that distinction, the parent and child will be processed or executed their corresponding execution paths and all, right? So this is the way the parent and child will coordinate and they carry out their execution sequences and all. Okay, so this was the fork system call and exec system call. So these are the system calls that are supported by the Unix operating system. Similar to that, in case of Windows also, there will be corresponding API. there are corresponding system calls like a create process, right? And there is other similar to that. The more or less the command, the overall process is same, but the way it implements will be different. So therefore, in case of Windows API, this is the code where you can able to see that how the process is created and process is terminated and all. You can see that. Okay, so next the process termination. So we'll stop here. So we'll continue this in tomorrow's lecture. So yeah, in tomorrow's lecture we'll continue this, and afterwards we'll discuss about the main another important thing is the process communication, inter-process communication. And so with that we can complete the process. So mostly in tomorrow's the double lecture, 2 hours lecture. So we'll try to complete the rest of the contents that are there in the process and all. So we stop here today. Let me stop the sharing. Stop the recording.